All right, so we're back to the Finnegans Wake problem now. And now we really understand how it works. Hopefully a lot of the code will make sense now that we've done the theory behind it. Now, if I run this and open up the console, at the moment you'll see that there's very little in the way of, there's no debug information, in fact, going on in the console. If you go into the code, and of course you've cloned it, you've edited it, you've got your own version, you can turn these constants on or off, and when you turn them on or off, or when you turn them on, you'll get debug information about different things that are going on in the console. So you can see how mutation is working, you can see how crossover is working, you can see how reproduction is working. So try that, experiment with the debug information as part of seeing how the entire system works, how it makes new individuals, how it decides their fitness, how it picks individuals for mating into the next generation. The next thing that you want to change is to get to work on some of these constants up at the top. So the population size is 100. Well, what if we made it 100 million? Is that better? Well, maybe the system can't cope with that. How about 1 million? Surely that's good. Or is it? Because if it's 1 million, the first 1 million are going to be random. So it's going to spend ages working with 1 million random solutions. It's going to be wasting loads of time looking at rubbish solutions. So just making population size huge isn't necessarily the answer to making a better search. We could just waste loads of time. The mutation rate, the number of times in reproduction, well, go and have a look, see when mutations happen. Mutations happen at a regular rate, and should there be more or less mutations? Change it to 1. What does that do? So answer in the comments perhaps, or have a discussion. Is that a good idea? Mutation rate 1? Does that sound right to you? How about mutation rate 0? What would that do? Or mutation rate 0.1. So is there a perfect mutation rate? Another one here is the relationship between fitness and score. So earlier we said that the score is how many characters the string has right. But if that's the fitness, you get a very strange search where basically they all kind of look the same fitness, and it doesn't really focus on the fitter ones, which is what it should be doing, and dropping the less fit ones because they're all more or less the same. So the idea of this power-based thing is to let it focus more on the very fittest. And the bigger you make this, the more it focuses on only the very fittest reproducing and dropping off anybody apart from the top one or the very top tier. So make power base 100. What happens? What happens to our search? Is that a good idea? Is the point? Or, should power base just be huge? What happens if you make it 1? So change these things. Put power base up, power base down, population size up or down, and see does it make for a better search or a worse search. So it's quite easy to make the search worse, and by moving these too far in either direction. So it's an empirical problem to figure out what a good heuristic is in order to search this space in a reasonable time that's available to you. All right, there's a few other things in the exercise, as you'll see when you go on to the exercise. One of them is there's always crossover. How about if you change it to just having a probability of crossover? So the crossover sometimes happens, sometimes doesn't. And what that would mean is sometimes you get clones of the parents, and sometimes you get new individuals that are a mix of 2 parents. So is that good or bad? But make it customizable so that the probability of crossover can be between 0 and 1, and then look at it at 0, look at it at 1. See how the search progresses. The probability of mutation is another one. We have probability of mutation built in. But one thing you could do to change it is to make the mutation high at the start and lower later on. So the thinking is at the start all the solutions are rubbish, so we want to change them drastically, they're all random. But as we go along, we don't really want massive mutations because we want to focus on what's good about our solution to have survived this far and make small mutations to look for something slightly better. So a general good strategy is to have high changes when you don't know much, and later on, when you want to keep alive some good solutions, smaller changes, smaller mutations. So do that. Make probability mutation change as time goes on. Another one which is nice is to make this a much larger block of text and see how the thing goes. Is it just impossible to do the first page of Finnegans Wake, for example? Or can you find some combination of parameters that can do that in 5 minutes? All right, so have fun with different solutions, maybe an entire page. And do remember that the genetic algorithm is not really for problems where you have a target, where you have a known solution that you're trying to get to, because if you know the solution, there's no AI needed. So what we're going to do in the next worlds that we will look at in week 4 is we're going to look at genetic algorithms applied to a problem with no known target.